Welcome to Study Loop.
We're going to apply Gauss's law to this Gaussian cylinder. Here, for part A, we can say that A is going to be less than R, which is less than B, and we can say that the electric flux is then equaling the electric field times 2 pi R L, and we know that the charge enclosed would be equaling the linear charge density lambda times L. This would be the charge on the length L of the inner conductor by the Gaussian surface. And so we can, the electric flux equals the charge of the enclosed divided by the permittivity of free space. This gives us that then the electric field multiplied by 2 pi R times L will be equaling lambda L divided by epsilon naught. Of course, this gives us then that the length is going to cancel out, and we have that the electric field is going to be equaling the linear charge density lambda divided by 2 pi R times the the permittivity of free space, or the permittivity of a vacuum. We can say that the enclosed charge is positive, therefore the direction of the electric field is, we can say, radially outward. For part B, this would be essentially the diagram. So we're going to apply Gauss's law, where for part B, R is greater than some length C, and we can say that the electric flux would be equal to the electric field times 2 pi R times L once again, and again the enclosed charge is equaling pi times L. This is going to give us here, as we can see, the enclosed charge, the magnetic flux, all are giving us the exact same values. So here, the electric charge is, again, the linear charge density divided by 2 pi R multiplied by epsilon naught. And here, the enclosed charge is, again, positive. So the direction of E would be, again, radially outward. So we can now, for part C, we have that within a conductor, the electric field is equaling 0. So we can say electric field equals 0 within a conductor. And we can then say, thus, the electric field is going to equal 0 for radii less than A. And so we can say that E is equaling the linear charge density divided by 2 pi R epsilon naught. This would be for A less than R less than B. We know that for E equals 0, for B less than R less than C, and then for R greater than C, we have that the electric field is equal, again, the linear charge density divided by 2 pi R multiplied by the permittivity of free space, or the permittivity of a vacuum. This is what it would look like, the electric field versus the radius. And we have between 0 and A, it is 0. Between B and Z, it is 0. And we have the curves between A and B and anything larger than C. So this would be your answer. This would be graphing it for part C. And we can then say that for part D, for the inner surface, we're going to apply Gauss to a Gaussian cylinder with radius R, where here B is less than R is less than C. And we know the electric field on the surface, so now we need to calculate the enclosed charge. So this surface lies within the conductor cylinder, where we can just say E equals 0, therefore the magnetic flux is equaling 0. So Coax's law, we can say that the enclosed charge is going to equal 0. Surface encloses equaling the linear charge density multiplied by the length on the inner conductor, so it must enclose H negative L on the inner surface of the outer conductor. So we can say that surface encloses charge lambda L on inner conductor. And so given this, it must enclose charge negative lambda L on the inner surface of the outer conductor. And so the charge per unit length on the inner surface of the outer conductor is, of course, negative lambda. This would be, again, charge per unit length, or the linear charge density, on inner surface of outer conductor. This would be your answer for part D. That is the end of the solution. Thank you for watching.